All right, so it is 3:30 and we can kind of get started. So my apologies, I'm for some reason a little bit more out of breath than I normally am on most lecture days, especially after finishing 207. So yeah, this is a little breathy. My apologies here. But anyways, yeah, I just want to talk about some announcements before getting started. So yeah, I posted the project specifications. So I posted that at the beginning of this week. And there is that Google spreadsheet for you to declare your group. So that the deadline for group declaration, I think I set that to be the 25th. So again, if you're having any issues, finding teammates to work with, definitely reach out to me or Jordan. You can, write your name down on that Google spreadsheet. You can post on Piazza. But again, my general preference is for people to work in groups of four. However, if you really want to work by yourself or you want to work with like a group of two, for instance, reach out to me and, we do have these 5 available like small group slots. And they are on a first come, first serve basis. So we've had 2 people already reserve 2 of those slots. If for instance, like if there was a data set that you really, liked working on, it was like part of, another research project that you were working on, and you really wanted to, focus on that. That's kind of what I envision, the solo group work to, essentially be about. So reach out to me if you want to request that slot, basically. And then so I spent all of yesterday working on this practice test. So this is actually the first time I'm doing a final exam for this course. So I think I created a pretty cohesive set of practice test questions, I guess you could say, that should look very similar to the style and the structure of questions that you might expect to see on the final exam. So if you combine essentially what I put on that practice test as well as the nature of the questions that you see like in the PDF part of the assignment, that should give you a good sense as to the types of questions that I might be asking you. But do take note, the exam is not going to be necessarily as long as the practice test. There's no coding on the exam. You can use a cheat sheet. I do see a hand raise. I'll get to that in a second. You can use a cheat sheet. You can write on the front and back. The only stipulation is that it's on like a normal sheet of paper, like 8.5 by 11. What you write on that cheat sheet has to be in your own handwriting, and you can't print anything out from a computer. So, when you take that exam, I will be inspecting it. So, any cheat sheets that aren't up to code, unfortunately can't be used. And yeah, I'm very close to finishing the solutions, I guess I'll say, but at the very latest, I will post those solutions by Monday night. And also keep in mind the units that the exam will cover are going to be units 1 through 15. So there's going to be 3 more units that we'll cover that will be on the exam. So, I would say the best way to practice for that additional content is take a look at that practice test. So I forget who was Charlie. I think you had a question, right?
Yeah, I couldn't find out when the final exam was. Is it like the last day of classes?
Yeah, it's the last day of class at
Oh,
3:30. Yeah.
thank you so much.
Yeah, and I haven't set up a room yet, but I'll reach out to you guys once I have that set up. Someone's asking, can I write on a tablet and then print it out? No, unfortunately, this has to be all, paper and pencil, if you will. Okay. All right. Cool. Any questions on that? Any questions before we get started? All right. So on Tuesday, we were talking about, or we began our lecture on Gaussian mixture models. And, one of the benefits that we are going to see with the Gaussian mixture model is that essentially it's going to be this much more rigorous, much more flexible extension of what we are attempting to do with k-means and fuzzy c-means. So like we discussed, we're relaxing, one of the assumptions that we had about the nature of the clusters that k-means and fuzzy c-means was designed to detect. So always remember, k-means and fuzzy c-means, they're designed to detect spherical clusters in particular. And now that we're actually getting into more, statistically rigorous language, what we're actually assuming about those clusters in k-means, fuzzy c-means, and Gaussian mixture models is that the data or the observations in each of those clusters were actually, observations that were randomly generated from a Gaussian distribution. So, one of the main, stipulations or constraints that we assume in k-means and fuzzy c-means is that the covariance matrix of those Gaussian distributions basically has zeros on the off diagonal, or in other words, there's no covariance between the attributes. And secondly, the variance of each of the individual attributes are all the same. So in Gaussian mixture models, we're allowing our assumptions to be much more flexible. We're allowing for both ellipsoidal clusters, or in other words, we're allowing for the variances of the attributes to be different. And furthermore, we're allowing for those, ellipsoidal clusters to not have to lay parallel to, the main axes, if you will. But, what we're seeing here is we also get this additional benefit in that when we actually are, performing Gaussian mixture model clustering, we actually simultaneously are going to be able to generate or fit a probability distribution that would have theoretically generated the data set that we actually have in our hands. And so, one of the things is, like the main thing that we are estimating when we, create that probability distribution is we're estimating, what would be the mean and the covariance matrix of each of these k Gaussian distributions, number one. And number two is, what would be the likelihood of selecting, one of these particular Gaussian distributions. But basically, once we have those estimates in place, we can use that information as well as Bayes' equation to estimate what we call the posteriors of a Gaussian mixture model clustering. Or in other words, given that we're considering this particular observation, we can calculate the probability that that particular observation came from that particular cluster or Gaussian distribution. Or in other words, we're calculating the fuzzy clustering membership score for that observation and that cluster. So, the way, in Tuesday's class, the way that we went about, approximating these means and these covariance matrices, as well as these priors, was very crude. We simply just used basic eyeballing. So the problem with this is that, this is this technique that we just, kind of used is it's, not statistically rigorous method for approximating these priors, means, and covariance matrices of the k Gaussian distributions, i.e. clusters. So therefore, rather than using this eyeballing method, we're going to use a much more statistically rigorous method, which we've seen before in Stat 410. We're going to use, or attempt to use, maximum likelihood estimation to estimate priors, means, and covariance matrices that maximize the likelihood of observing the data set that we actually have in our hands. Okay, so that's the first goal, to come up with those Gaussian or those cluster parameters. But then first and foremost, the primary goal is to use those estimates to calculate the probability that a given observation was or came from each of the k Gaussians or clusters. Or in other words, calculate the fuzzy clustering membership scores. Okay. So that's what we're going to do here with Gaussian mixture modeling. And so Gaussian mixture modeling is actually a specific type of a mixture model that we could, or a particular type of a mixture model, essentially. So a general mixture model essentially comes with a particular assumption about how a particular data set was generated. So first, what we assume, so basically, let's just say we have M observations in our data set. So we assume the process for generating each of those observations is as follows. So first, we randomly select one of K distributions. Okay, and we're not stipulating that these distributions are Gaussian. They could be, at the moment, any type of distribution that suits. So it could be like truncated normal or something like that. And we assume that there is a set of priors, or in other words, a set of probabilities that dictate the likelihood of randomly selecting any one of those particular distributions. So generally speaking, this is going to be a set of parameters that we try to estimate. And so let's just say we've randomly selected a particular Gaussian or cluster. Then we use the information about that Gaussian or cluster, i.e. the means and the covariance matrix, to randomly generate a point from that distribution, so on and so forth. So we basically keep this going for every observation in the data set. So based on this data generation assumption, there are, under a general mixture model assumption, there are three things that we are attempting to estimate. So number one, we're trying to estimate these priors, i.e. the probability that we randomly select any given Gaussian distribution for a particular observation. And number two, we're trying to select the corresponding parameters that correspond to each of these distributions. And then finally, in the general case, we also are trying to estimate, the type of distribution that each of these basically the type of distribution that any one of these distributions are, essentially. So this could be normal, it could be truncated normal, it could be anything. We leave it open. So under this random, data generating process, if we want to, for instance, estimate or calculate the PDF or the underlying model or the PDF for randomly selecting a single observations under this data generating process, then we can calculate that PDF as such. So this represents the probability of randomly selecting a given observation under a set of parameters that we're assuming here. And so we can represent that PDF as such by marginalizing over all possible distributions it could have been drawn from. So this could be the probability of X given that X was drawn from Gaussian 1, probability of X given that this observation was drawn from Gaussian 2, so on and so forth. And we can then represent this joint probability is the following by using the general multiplication rule. Where this is actually simply, or this can simply just be reflected for a given Gaussian cluster K as simply just the probability of randomly selecting the kth Gaussian, or excuse me, the kth distribution times the probability of randomly selecting that particular observation, given that we know that it was drawn from the kth distribution. And so this is where our priors come in that we were trying to estimate. And then we also call these priors, so this has another name. We call these the mixing weights of a mixture model. Okay, and so given that, there's, basically given that these mixing weights or these priors are a probability distribution, these mixing weights or these priors do have to, add up to 1. Okay. And so, what this expression here actually represents is, for instance, if we were assuming that that particular distribution was a Gaussian, then what this value here represents under this scenario would be the PDF of a Gaussian distribution with that particular set of means and covariance matrices. Okay. And so, using this PDF, which corresponds to just a single observation from that data generating process, we could use that, for instance, like we've seen in some of our 400 level stat classes. We can use that, for instance, to calculate the probability that a given observation, calculate the probability that the probability of randomly selecting a value which is at most 4.9 and 10. So, in other words, that would be we would use that PDF to help us calculate the probability of randomly selecting an observation from this data generating process that showed up in this region here. And so we can use our 400 level statistical techniques that we've learned to basically integrate over that PDF. I'm going to take this here. Yep. So in this particular case, for instance, we would be integrating that PDF over X and Y. Okay, so this could be, this is one reason or one benefit of, using this much more statistically rigorous method of a mixture model, in that not only does it, allow for you to cluster a given data set, but it also allows for you to, calculate the probability that, a given randomly generated observation falls within a certain range. So that might be beneficial to you. Now, this is simply just the PDF, which allows for you to calculate the probability that a single observation of this data generating process falls within a certain range. But actually, given that we're going to be using maximum likelihood estimation, what we'd actually like to calculate is the underlying model for an entire data set, or in other words, calculate a PDF for M randomly selected observations, assuming that same data generating process where we have K distributions, each with their own set of K corresponding parameters. And then we're also making the assumption that each of these observations were drawn in an independent manner. So if we're making all of these assumptions, then we can model this, or the PDF, for randomly selecting all of these M observations to be the following. So this would be the PDF for all observations in our data set, assuming the corresponding distribution parameters. And again, because we are assuming that each of these observations is drawn in an independent manner, and simply just represent, or this is simply just the product of all of the individual PDFs, assuming those Gaussian parameters. And we can simply just plug in the mixture model representation for each of those M observations in the data set. And therefore, what this PDF gives us is a way of calculating the probability that M observations drawn using this random data generating process fall within a certain range, which might be beneficial for a wide variety of purposes, if you will, if you want to be more statistically rigorous. Okay. Any questions so far? Okay. So that is, general mixture models. And so, um, when we're using Gaussian mixture models, we relax one of the things that we are attempting to estimate. So in a Gaussian mixture model, we assume that the type of distribution that each of these K distributions are is in fact a Gaussian or a multivariate normal. So for the purpose of cluster analysis, how might we check if this is a good assumption to make? So questions for you guys. So for instance, if the two-dimensional data set had like a set of observations that looked like this, would assuming that these observations was generated from a Gaussian distribution, would that be a good assumption to make? No, yeah. So yeah, if a set of observations was randomly generated from a Gaussian distribution, then what we would expect is for those observations to have an ellipsoidal shape. So we say that observations drawn from a Gaussian distribution have ellipsoidal shapes. So if that's the case, what might we consult to see if that's a fair assumption to make that our cluster shapes are ellipsoidal? So what's the technique that we use to evaluate or the shape of any given cluster in our analyses so far? Yeah, exactly. TSNE plots. So we can check a TSNE plot, check TSNE plots to see if the clusters are ellipsoidal. Okay. So if we feel comfortable making that assumption about our cluster shapes and therefore our distributions being Gaussian, then this makes our job of mixture models a little bit easier because there's one less thing we need to estimate. So now all we need to estimate are the priors and the mean and the covariance matrices of each of our K Gaussians. Okay. Now, actually, unfortunately, what we're going to see is that even though we've relaxed one of our assumptions, the actual task of analytically estimating all of these parameters together is actually impossible. Or in other words, there's not a closed form solution for how we can exactly calculate all of these three different types of parameters. But to showcase how we might go about, calculating these optimal parameters under a additional simplified assumption, here's how we might go about doing this. So basically, this is not a realistic version of Gaussian mixture modeling because we're making it, for now, a simplifying assumption in that we also actually know what our priors are going to be. So let's just simplify this problem for now. Let's just say we can assume to know ahead of time what these priors are, and also that they're going to be a 1 or a 0. Or in other words, for each of these observations, we know what cluster it actually came from. Now, this is kind of a boring assumption, right? Because basically the whole point, or one of the main points of fitting a Gaussian mixture model, is to allow for us to estimate the probability that each of these observations was drawn from a given cluster. So essentially, what we're assuming here is that, we already know the answer of what cluster the observation came from. So this is kind of boring and a little bit, useless from an analytical perspective or practical perspective, but we're going to show, how this would theoretically work if our more realistic scenario was not analytically intractable. So here's how we would proceed when it came to estimating our final set of parameters that we don't know, so the means and the covariance matrices. So ideally, or what we can use, as we've seen in stat 410, is maximum likelihood estimation. Or in other words, we'd like to estimate the optimal set of means and covariance matrices for each of our K clusters that maximize the likelihood of observing the actual data set that we have in our hands. Okay, so each of our M observations. And so therefore, we've already came up with a slightly easier to use representation of this probability here. So we're simply just multiplying the individual probability for each of the individual observations. Okay, and now we're simply just representing each of these individual probabilities with the mixture model representation. So with our mixing weights and each of the posteriors here. And now this is where our simplifying assumption is going to come in handy, because basically without the simplifying assumption, we kind of get stuck in this part here, unfortunately. So given that we actually know what our priors are, this is either going to be a 1 if that particular observation that we're considering is in that particular cluster K that we're considering. Otherwise, it's going to be a 0. So basically, because of that, we can simplify this entire expression here as simply just being the product of all observations, or basically the product of the probability of a given observation, assuming that it belongs to cluster K. And again, this is where we actually know the answer. We actually know if a given observation, belongs to that particular cluster. Okay, so this kind of a boring scenario. And so what we can actually see here, so for instance, let's just take a look at this different optimization problem here. So if we know that, we're trying to maximize a given objective function, which is basically a product of expressions that only involve one and only one decision variable, then we can actually, what this optimization problem is actually equivalent to is simply just the product of two optimization problems. So all we really need to do to solve this more complicated optimization problem is actually maximize this function with respect to theta 1, find that optimal value, and then do the same thing for this expression and theta 2. So basically multiply those two optimal values together. So therefore, this is kind of the idea that we're using to basically actually turn this single optimization problem into simply just the product of K sub-optimization problems. So we're simply just going to find the optimal Gaussian parameters for a single Gaussian distribution, find that optimal probability for that cluster, and then multiply all those probabilities together. Okay, so we can be a little bit more specific here. And so these theta K parameters are actually the means and the covariance matrices of that Gaussian. Okay, and then here, what this actually represents is the PDF of that particular kth Gaussian here. So we can actually, write out that PDF expression. Okay, and so really all we need to focus on now is how we can find the optimal mean and covariance matrix for each K optimization problem. So let's focus on just the kth sub-optimization problem. Okay, so as we've seen, when we've talked about maximum likelihood estimation, if you're trying to calculate, so this essentially would be the point where you would, try to calculate the gradient of this entire expression here with respect to the mean and the covariance matrix. However, as we've seen in calculus, calculating the gradient or the derivative in general of, a bunch of products is, it's more challenging, if you will. So therefore, what we typically do in maximum likelihood estimation is we say, well, okay, I know that this is actually an equivalent optimization problem. So if I simply just calculate the log of this likelihood, then I know that the optimal, or basically the optimal solutions that maximize this are going to be the same optimal solutions that maximize this. So I'm going to make life easier for myself. So I'll take the natural log of this and optimize this problem. And again, as we've seen in Stat 410, this makes things nice for us because a natural log can basically split up a product as such, as we've seen with our natural log properties. Okay. And so we get a little bit of some cancellation here. Okay. And yeah, but basically this makes this task of differentiating this expression with respect to the mean and the covariance matrix much more easy. So we differentiate this function, we set it equal to 0, and we solve for our mean and covariance matrices for that particular Gaussian distribution. Okay, and so under this, very boring, unrealistic scenario, the estimated mean and the estimated covariance matrix, they make sense, right? So the estimated mean of a particular cluster is simply just the mean of all the observations. And the estimated covariance matrix of a particular cluster or Gaussian is simply just the covariance matrix equation for a given data set. So a lot of this makes sense here. Okay, so generally speaking, in a Gaussian mixture model clustering or cluster analysis, we've essentially solved goal 1 of our analysis. We've estimated the unknown parameters of the data generating process. And so therefore, that gives us a particular, PDF for, modeling the likelihood that a given observation, or a given set of observations falls within a certain range. But for the purpose of cluster analysis, the next step is to actually cluster each of our observations in the data set. So, what we do using those parameter estimates that we have just calculated, we calculate the posteriors for a given observation in a given cluster. So we say, given that I know that I'm dealing with, this particular observation in my data set, what's the likelihood that it was drawn from the kth Gaussian in that data generating process? So we can use Bayes' equation, just like we did on Tuesday, to basically calculate what that probability is. And so again, what this represents is the PDF of the kth Gaussian. Okay. And since we now know, or since we have now estimated all of the corresponding means and covariance matrices of those Gaussians, this is something that we can calculate. We simply just plug in that observation to the PDF of that corresponding Gaussian. And we also incorporate the priors. Okay, now this is something that we assume to know ahead of time. So actually, this turns into a very boring calculation as well. So, if a given observation, does not belong to that particular cluster, which is something that we assume to know ahead of time, like i.e. we knew the answer key, then this prior would simply just be a 0, and therefore this would be 0. So it's like we assume to know it was drawn from cluster K, and our posterior is also saying that it's not drawn from cluster K. And similarly, if we assume to know ahead of time that, a particular observation was in fact drawn from cluster K, then the posterior also ends up being a 1 as well. So it's kind of telling us things that we already knew. So not super exciting. Now, the more practical scenario, or the general version of Gaussian mixture models, is where we don't assume to know what these priors are. So this is another thing that we need to estimate. Or in other words, we want to estimate the likelihood of randomly selecting any one of these Gaussians in our data generating process. So we might set about to perform that same maximum likelihood estimation, in which we're now trying to estimate the priors, the means, and the covariance matrices. So we would set up the same optimization problem. However, unfortunately, we run into a problem in which this optimization problem is actually not analytically solvable. There's no way to actually get a closed form solution, to actually calculate these theta and W parameters. In other words, calculating the gradient of this expression here, unfortunately does not, or calculating the gradient and setting it equal to 0 does not yield a closed form equation that can be solved, unfortunately. However, we have other ways of going about attempting to find the optimal solution to this optimization problem. So we rely on heuristic algorithms, as we've seen with many of our other clustering algorithms, which ideally are attempting to solve an optimization problem. And basically, the main idea behind the heuristic algorithm that we're going to introduce in just a second is that basically, if if we knew the posteriors so basically these values here ahead of time, then we would be able to calculate a closed form solution to this optimization problem, which would thereby allow us to estimate the priors, means, and covariance matrices of the K Gaussians, right? And then, if we actually knew what so the problem is, we don't know what those posteriors are, but on the other hand, if we knew what the priors, means, and covariance matrices were, then we could calculate these posteriors. So basically, both of these two equations has something that the other equation needs. So we utilize that relationship in the expectation maximization algorithm to attempt to basically iteratively solve for these two sets of things that we're trying to solve for, to basically approach the optimal solution to this maximum likelihood estimation. And so we call this the EM algorithm, and we're applying it to the purpose of fitting our Gaussian mixture model. But the EM algorithm can actually be applied to a wide variety of different objective functions that you might be trying to maximize, if you will. But as we're going through this EM algorithm, let's take note of some of the similarities that we're seeing with K-means and fuzzy C-means, because there's going to be a lot of overlap. So when we're applying the EM algorithm for the purpose of fitting a Gaussian mixture model, excuse me, our input is simply just our n-dimensional data set with m observations, and much like we saw with actually all of our prototype-based clusters, we do need to stipulate the number of clusters that we would like, i.e. the number of Gaussians that we would like to assume that there is. And then basically our final output is the clustering, or the posteriors of each of the observations and each of the clusters, which you could think of as the fuzzy clustering membership score of a given observation and a given cluster. Or in other words, the probability that this given observation was drawn from the kth cluster or Gaussian. Okay, so to run the EM algorithm, we start with our initialization step. Now, rather than initializing the centroids, so this is sort of like the centroid initialization step. So rather than simply just initializing the centroids, i.e. the means of our k Gaussians or clusters, we're also initializing all the other parameters that we aren't assuming to know ahead of time. Because we're assuming that the covariance matrix can be anything, we also need to randomly initialize each of the covariance matrices as well as our k priors. Okay. And then, oops, we repeat the following two steps until a certain stopping criterion has been met. So the first step is the expectation step. And this is basically like our fuzzy clustering or our cluster assignment step, in which we are assuming to have like the centroids, or in our case, in which we're assuming to have the means, the covariance matrices, and the priors of each of the k clusters. And we're using that information with Bayes' equation to calculate each of our posteriors, or in other words, calculate the probability that that given observation came from cluster or Gaussian 1, 2, 3, 4, however many. So we can think of these, basically what we're calculating here is the fuzzy clustering membership scores. And so, given that we were assuming to know the parameters, we can in fact actually, use these equations to calculate the posteriors. And then now that we have these posteriors, our optimization problem, in which we are solving for the optimal parameters that maximize the maximum likelihood estimate, we can in fact now analytically solve for these parameters if we assume to know what these posteriors are. And so we're not going to go into the calculation of the gradient, the actual solution, but basically when you calculate the gradient of this with respect to these three parameters, assuming that this is known, then and you set those gradients equal to 0 and solve for these parameter values, this is what you end up getting here. And so basically this maximization step is basically like the centroid update step in k-means. But now in this case, rather than just updating the centroid or the means, we're also updating the covariance matrices as well as the priors. So I see a question here, so I'll get to that in 1 second. But let's try to put into words these equations here. So in the maximization step, I'm estimating the prior for cluster K, i.e. the probability that cluster K, or excuse me, the probability that a given observation is drawn from cluster K. I'm estimating it to be this. So how would we put this expression into words? Given that like this is the posterior of a given observation being drawn from cluster K. So what does like this usually convey? Yeah, yeah. So what we're doing here is um, calculating the average posterior or the average of the kth posteriors. Mhm. Yeah. And then what about this? So basically, I'm adding up all of my observations in the data set. And then here are like all of my kth posteriors here. Yeah, it's like it's a weighted mean, right? So we when we were calculating the centroid and fuzzy c-means, right, we were also calculating the weighted mean. We're basically all of my kth posteriors are the weights. So this is the weighted mean of the observations in the data set, where the weights are the kth, all the kth posteriors. Okay. And then I'll just kind of cut to the chase with this term here. So what this actually represents is the weighted covariance matrix of the observations in the data set, where again the weights are all the kth posteriors. Okay. Um, so basically all we're really utilizing here is the posteriors, which we're assuming to know at the moment. Okay. And so much like we saw with k-means and fuzzy c-means, as well as all of our heuristic algorithms, which use this cluster assignment step, parameter update step iteratively, we keep going until the parameters don't change. Okay. So I saw a question here. What are some common preset starting values for the initialization step? I mean, I think there's, scikit-learn probably has more sophisticated techniques that it runs on the back end. So if you wanted to explore this more, you could kind of dig into some of the documentation for Gaussian mixture models on scikit-learn. But yeah, generally speaking, I mean, the way to generate like the center or the means would be, the same techniques that you would use to generate the initial centroids for k-means. I mean, you could, for instance, like, a very basic technique would just be to, draw from the uniform distribution, where the uniform distribution is set between like the min and the max value for each of the attributes, for instance. If you wanted to randomly generate like a probability distribution, which represents your priors, one way that we go about doing this is there's a symmetric Dirichlet distribution, which is basically a probability distribution that allows for you to randomly generate actual like probability distributions themselves. So those are some techniques that you could, for instance, use for the mean and the priors. And then the covariance matrix, you can use, like for instance, like if you wanted to, you could start out with a covariance matrix in which like all of the covariances were 0. And for the variances, you could, randomly generate like a couple of values that, fell within a certain range that you've observed in your data set, for instance. So there's a lot of things that you could do. Some are more or less effective, but that's, some ideas. Cool. Any questions on that? All right, so this is the general algorithm. So we wanted to, for instance, go through just one iteration of this algorithm as an example. Then, so for instance, let's just say we wanted to initialize all of our means, covariance matrices, and priors using the eyeballing method that we used in the last class. So let's just say we've decided to do that. So this is the set of parameters that we're currently assuming belongs to each of our k Gaussian distributions. And then we move on to the expectation step. So let's, for instance, just calculate the 4 priors for, let's just say, this observation here in the data set. Now, we would actually do this for every observation in the data set, but we'll just focus on this observation here. And so this is also a calculation that we did on Tuesday. So to calculate the probability that a given observation came from cluster zero, assuming that basically cluster zero has this particular set of um, means, covariance matrices, as well as priors. Um, then we can just simply use Bayes' equation as we've seen before. So this is basically, what you get when you plug in that particular observation into cluster zeros Gaussian distribution, where we're assuming that it currently has this mean and this covariance matrix. So we get this value here. And then we multiply it by the current prior for that cluster zero. We're currently assuming this to be 0.25. And then we basically do that for, in the denominator, we do that for all of the K Gaussians as well. Okay, so that currently gives us an estimate or a posterior of 0.45, or in other words, the likelihood that observation 7 was drawn from the first, or basically cluster 0, is 0.45. So we would do that for all of the 4 clusters for observation 7. And so basically all of these probabilities will add up to 1. So this gives us a probability distribution for observation 7. Okay, and so we would do that for all of the observations and all of the clusters. So giving us a current set of posteriors. So we would have those here. And now we move on to the maximization step to calculate the or estimate the parameters that optimize the log likelihood function, assuming that our posteriors are the actual posteriors. So we saw that. So for instance, if we wanted to calculate the optimal value of cluster 1's posterior, what we would do is, like we discussed, calculate the average of these values. Okay. All right. And let's just say we wanted to calculate the mean, the current estimate of cluster 1's mean. Then what we would do is we would calculate the weighted average of all the points in the data set, weighting those points by each of the cluster 1 posteriors. Okay. And finally, if we wanted to calculate the current estimate of the covariance matrix of Gaussian 1, then what we do is calculate the weighted covariance matrix of all the points in the data set, and we would be weighting by the Gaussian or cluster 1 posteriors. Okay. I saw a private message about the secant method. If you wanted to email me that question, that is a good question. I can follow up with you after class. Okay. Cool. So any questions on that? All right. So we'll get to the benefits and drawbacks of each of these techniques probably on Tuesday, but I did want to get started on the application here in just a second. So something that we wanted to think about is, well, how might we go about selecting the the best number of clusters to look for in our Gaussian mixture models? So, we could rely on some of the techniques that we've used in the past. So let's actually generate some other techniques first that are kind of based on what we've seen before. What would you guys say? Based on what we know already, what are some ways that we could go about coming up with a sensible number of clusters to ask for in Gaussian mixture models? Yeah, so I'm seeing one person say elbow plot method. Yeah, so that is one technique that we could use. And so you want to remember, in a corresponding clustering algorithms elbow plot method, the thing that we want to put on the y-axis is the thing that, or the objective function that we are trying to ideally optimize. Okay, so the thing here is that the thing that we're trying to optimize here is the likelihood function. So the likelihood function, as we increase the number of clusters, the thing here is that the likelihood function is actually always going to be negative. So the interpretation becomes a little bit or slightly different here. But basically, the more parameters you add to your model, the closer your likelihood function is going to get to 0. So basically the perfect, the best fit scenario for the log likelihood function is that it's equal to 0. Or in other words, the likelihood of observing all of the observations in your data set is 1. And so the log of 1 is 0. Okay. So, your plot is it's not gonna look like this, like we've normally seen, but you could look for, leveling out points like in this fashion. And that might give you an indication of, how many clusters exist. Yeah, and then I'm also seeing a private message. Somebody also said TSNA. So actually, I think I'm going to put elbow plot method into quotes because actually, it's slightly, the curve is flipped. It's not the typical curve that we end up seeing. But yeah, we can also use the TSNE plot as well. I think I'll skip over this here for now. But basically, yeah, so the thing that we want to realize is that actually, the more clusters we assume are in our data set, the better of a fit our data set is going to be. Or in other words, the closer that log likelihood function value is going to get to, or it's going to approach 0. Now, if we wanted to have a perfect fit of our data set, we could actually assume that, the number of clusters in our data set was exactly equal to the number of observations in our data set. So if we made that assumption, then our fit would actually be perfect, or our log likelihood function value would be 0. However, in a scenario or a situation like this, if we think back to some of our other stat classes, we would be dramatically, overfitting this data set or overfitting this model to the data set that we actually have in our hands. And so, for instance, if we were to, incorporate another observation that was not in this same data set and try to calculate the probability that it came from any particular one of these clusters, we would expect worse performance. So therefore, another technique that we can use to help us try to select the right, if you will, or the inherent number of clusters that might exist in a Gaussian mixture model is to use parsimoniousness metrics like we've seen in some of our other machine learning models. In other words, we can use metrics that, basically play this balancing act of, encouraging our model to have a good fit, but at the same time, encouraging our given model to have not a whole lot of parameters that don't really improve the fit all that much. So the two metrics that we're going to talk about, and you might have seen them before, and you may have not. So we're going to introduce the Akaike information criterion, i.e. the AIC score of a given model, and the Bayes information criterion, i.e. the BIC score of a given model. And so the thing that these two metrics, what they measure, is they measure the overall parsimoniousness of the model, i.e. the extent to which a given model achieves this ideal balance of, not underfitting a model, but not overfitting a model as well. So in theory, a parsimonious model is going to be the model that's going to give you the best fit, not necessarily for the data set that you have in your hands, but for new data sets that are theoretically drawn from the same data generating process. So someone's asking, can we take the absolute value so it becomes symmetric to the other side of the axis? Yeah, I mean, so for instance, if you wanted to instead, like just simply put a negative in front of the log likelihood function value, then that would reflect this about the x-axis and would look like the standard elbow plot that you've seen. So yeah, that's something that you can do as well. Yeah, it's a good idea. So so the Akaike information criterion is calculated as follows. So we incorporate the 2 times the number of parameters in the model minus 2 times the log likelihood function value. Okay, and basically the way that the AIC score works is as follows. So let's just say, for instance, we are considering whether we should add an additional cluster to our model. Is it worth it? Is it possible that, if we add an additional cluster, could we start perhaps splitting up some of the natural inherent clusters? So inevitably, if you add another cluster to your Gaussian mixture model, the number of parameters that you need to estimate in that model is going to increase. However, if you include an additional parameter, you're giving your model more of a chance, if you're including an additional Gaussian to your model, you're giving your model more of a chance to achieve a better fit. So therefore, your log likelihood function value is going to increase, i.e. become less negative. And therefore, the negative version of that log likelihood value, or negative 2 times that log likelihood function value, it is going to decrease. Now, the question is how much of a improvement or a decrease in negative 2 log likelihood function value you're going to get. So the thing here is, if you decide to add an additional Gaussian and the decrease to the negative 2 log likelihood value is large in comparison to this increase, then what that means is that your AIC score is going to decrease overall. On the other hand, if the improvement to the fit of your model, when you include that additional Gaussian, is only, comparatively very small, then what that means is that overall your AIC score is going to increase. So the idea is that, if we're actually picking up on additional natural existing clusters in your data set, then we would expect to see a dramatic decrease, or basically a dramatic improvement to the fit. So therefore, we would expect to see the AIC decrease. So therefore, in general, the lower the AIC score, the more parsimonious the model. Or in other words, the model is more likely to achieve a good fit for new data sets. And for the purpose of Gaussian mixture model clustering, it means we're more likely to be detecting naturally existing clusters in the data set. Okay. So on the other hand, for instance, if your fit were to really only decrease or improve just a little bit, and therefore your AIC score increased, then what that might suggest is that at that point, we might be splitting up some of the natural clusters that exist. Okay. So someone's asking, so our goal is to minimize AIC. Yeah, that's correct. So, sorry. Yeah, so just to kind of recap what I've talked about so far, the general idea behind the AIC is, excuse me, one way of measuring and optimizing the number of searched for parameters in a model to achieve one definition of a parsimonious model, which is a model that achieves an ideal balance of minimizing the number of searched for parameters and simultaneously maximizing the fit or the likelihood of observing the observations in our actual data set. And essentially, it helps the model to not overfit the data, thereby giving us a better chance of selecting actual meaningful inherent clusters that exist in our data set. Okay, but the thing here is you want to be careful about how you're using that AIC score. So the AIC score should only be used when you are evaluating models derived from the same data set. Okay. Yeah, so the log likelihood function value is always non-positive. So therefore, -2 times the log likelihood function value is always going to be non-negative. So our overall goal, if we want to achieve the best fit possible for this -2 log likelihood function value is to basically get this value as close to 0 as possible. Oh, goodness, sorry, I'm running out of time. Okay, so I'm going to skip over this part here. So one of the downsides of using the AIC to measure parsimoniousness is that it does not tend to work as well for small data sets. So unfortunately, sometimes what we can end up seeing is a set of AIC scores that look like this. So let's just say, for instance, we calculate the AIC of one Gaussian mixture model with one cluster, do it for 2 clusters, 3 clusters, 4 clusters. Well, ideally what we'd like to see is something like this, where, we see this valley, if you were a local minimum. And so this would be the indication that, this is the K value that gives the most parsimonious model. So this is an AIC and K curve that we would like to see. It's going to be the most, insightful one. Unfortunately, sometimes what we can end up seeing, especially for small data sets, is instead something that looks like this, where we never actually get like a local minimum. So what this plot is actually suggesting to us is that the more, clusters you add, the more parsimonious this model is. Or in other words, the more clusters you add, the better a fit this model will be for new data sets. So that interpretation kind of flies in the face of, what we know about overfitting. We know that eventually, if you keep adding complexity to a given model, eventually you're going to start overfitting a given data set and you're going to get worse performance for new data sets. Or in other words, you're going to start overfitting. So, this is, if you see something like this is, telling you AIC is probably not the best metric for measuring the parsimoniousness of a model. So someone's asking a question. So when plotting AIC, BIC over K number of clusters, since you have to refit the data to K clusters every time, how much influence does the random state have? Yeah, I mean, I think it depends on the data set that you're working with. So if you want to minimize the influence of the random state, you could try, multiple random states and calculate the average AIC, for instance. Yep, that's a good question. So, if you're, oh, sorry, one other thing. So a general rule of thumb for roughly determining, if your data set is too small is to check if this inequality is met. So in other words, if the number of, actually, let me change this here. The number of observations in your data set, M, divided by the number of parameters that you're trying to estimate. If it's greater than 40, then AIC tends to be better. You're, less likely to get something that looks like this. Otherwise, it's possible that you might get these very uninformative AIC plots. So someone's asking, may I know why in this case it is not proper to find a K where the most decrease occurs, like an elbow? Yeah, so for instance, like if this is the only plot that you have to rely upon to give you the best estimate as to what the ideal number of clusters might be, you could, then start looking for these points, like the elbows of diminishing returns. But generally speaking, if you see a plot like this, what that indicates is that the AIC score has kind of failed to measure what it is intended to measure. So I might suggest using other metrics instead, but you could try to interpret that elbow plot as like your best guess as the number of clusters. Yep, that's a good question. So we also have a different parsimoniousness metric that we could use, and it's very similar to AIC. So we also introduced the BIC score. And the only difference between them is the penalty term that we place in front of the number of parameters in the model. So we might want to ask ourselves, under what scenarios or under what sample sizes is there going to be more of a penalty for the number of parameters in the BIC score? So to answer this question, you would be asking yourself, under what sample sizes is the natural log of n greater than 2? So you can exponentiate both sides. And so what that tells us is that for sample sizes that are greater than 8, which is basically pretty much any sample size that you might be dealing with, this penalty is going to be larger. So what that means is that the BIC score, if you're selecting the model with the lowest BIC score, your model is going to penalize having a high number of parameters more. So therefore, if you're using the BIC score to select, then your resulting Gaussian mixture model is probably going to have fewer suggested clusters to use, essentially. Okay. Yeah, but the way that you interpret the BIC score is the same as the AIC score. The lower the BIC, the more parsimonious the model, i.e. less likely it is to overfit. And in the case of Gaussian mixture models, less likely to split up meaningful clusters, in theory. But again, we want to be careful about how we use that BIC score. So the BIC score of a given model should only be compared for models that are derived from the same data set. Okay. Questions on that? And yeah, so the thing here is like the BIC score, you're less likely to get scenarios like this, where the parsimoniousness metric sort of violates its own properties that it's trying to measure. So if you see the AIC score giving you something like this, you might try the BIC score. However, this does come with a downside. So given that the BIC score more strongly penalizes having a high number of parameters, what that means is that models selected with the BIC score may be less reliable, or in other words, the model fit might be worse. Okay. All right. Questions on that? Okay, very quickly. Unfortunately, I might have to add on some additional content after class. Sorry, guys. But very quickly, I want to get through some of the application. Okay. So yet again, we are using the MNIST data set. And we're going to use Gaussian mixture models to now cluster the MNIST data set. You might think about a couple of reasons for why we might, in particular, want to use Gaussian mixture models. So for instance, if we take a look at the TS&E plot, we can see, some of these clusters are actually not all spherical. So that violates, the ideal property or the assumption that we were making with fuzzy C-means and K-means that all of our clusters were spherical. So it might be the case that by using Gaussian mixture models, we might more effectively be able to identify, these ellipsoidal clusters that we can see suggested here in the data set. Now, furthermore, one potential reason for why we might want to use Gaussian mixture models over fuzzy C-means is, you want to remember, in Gaussian mixture models, the only parameter that we pre-select ahead of time is the number of clusters. So let's just say, for instance, we didn't want to go through the process of, selecting the best fuzziness parameter in fuzzy C-means. Well, a potential benefit and drawback of Gaussian mixture models is that you're actually not allowed to select the fuzziness parameter. So if you have no idea what that ideal fuzziness parameter might be, maybe Gaussian mixture models is for you. On the other hand, it might be the case, as we're going to see here, is that the Gaussian mixture model does not allow for the type of fuzziness that you think would be most appropriate. So that can also be another downside. But one of the main benefits of Gaussian mixture models is that it gives us a much more rigorous statistical model for what we assume might have generated this data set here. So with that, we get this added bonus of fitting a probability distribution that would have generated this data set. And then with that, we can essentially randomly generate new observations that follow the same, general trends or properties of this data set here. Ooh, I'm running out of time. Okay, so very quickly, if you want to just perform a naive cluster analysis with Gaussian mixture models, you can use the Gaussian mixture function. Let's just say, for instance, I'd like to just start with 10 Gaussians or 10 clusters. And again, this is a non-deterministic algorithm, so it's a good idea to set a random state. So I've set up all my parameters, instantiated a Gaussian mixture object. And when I'm ready to fit it with my MNIST data set, I can use the fit function. Okay. And the syntax is a little bit different for Gaussian mixture models in this case. So for instance, we simply want to just spit out your posteriors, i.e. your fuzzy clustering membership matrix for this Gaussian mixture model. And then you can use the predict proba function. All right. And so what this gives you is the set of posteriors for every observation in your data set. In other words, the probability that this given observation was randomly drawn from each of the respective clusters. Okay? Or in other words, for all intents and purposes, a fuzzy clustering membership matrix. So what we can see here is that this is a very hard assignment, just by looking at these first few rows here. And furthermore, by using code that we've seen before already, this further validates this for us. So basically, almost every observation in the data set 100% belongs to one and only one cluster. So, if we wanted to reflect more of the uncertainty that certain straddle nodes should have with respect to a cluster membership, Gaussian mixture models was not very useful. It didn't reflect any uncertainty at all. So this might be an indication that fuzzy C-means is for us. Okay, so that's it. I've gone over. So I'll stop there. So I'll stop recording. Unfortunately, I need to add maybe like 10 additional minutes of content after class. So I will post that when it's ready. But yeah, otherwise, that is basically it. So I'll stop recording.